Okay. Open up your book. I'm going to start by just reading a short section that kind of introduces what a titration is. 713 is where we're going to be reading from. Okay. Bottom of the page, 15.4 is where I'm starting on 713. All right. As we saw in chapter 4, a titration is commonly used to determine the amount of acid or base in the solution. This process involves a solution of unknown concentration, which is known as the titrant, delivered from a burette into an unknown solution. Just quickly, let me see if there's a picture of a burette here. Basically what a burette is a really long glass tube that has, pretty precise tick marks so that you can measure the volume really well. Then it comes to a point, there's a little knob in here that closes and opens it and allows drips just to come out slowly or fast depending on how much you open the nozzle, which will allow you to, if you want, to just add one drop at a time, or if you want to add more, you could fully open it and let a decent stream come out. We did this a lot in college when we were doing labs with titrations. It was fun to see it, all of it, because of the color change when we used an indicator, but it was painstakingly long because you would sit and you would let one drip go in, measure the pH. Let another drip go in, measure the pH. Let another drip go in, measure the pH. And you would have 400 data points. That would just be annoying as heck. But that's what you had to do if you wanted to solve for an unknown, you were titrating some unknown acid that you want to know the concentration of. Okay, now we're not going to be doing unknown stuff. We're actually just going to be titrating with known stuff just to get the feel of what the process looks like mathematically. Okay, but yeah, that's what a burette is. You would put what your known stuff is, and you would titrate into a solution that you do not know the concentration of, using the idea that acids and bases neutralize each other. Okay, let me finish reading here. The stoichiometric equivalence point is often signaled by a color change of an indicator. What that is usually they will put in some sort of chemical that when the pH goes from basic to acidic or acidic to basic, you notice a color change. Right? It indicates when you've completely neutralized your unknown. Because if we completely neutralize our unknown, what would be our pH? 7. Okay? In this section, we will discuss the pH changes that occur during an acid-base titration. We will use the information later to show how to appropriate indicator, how an appropriate indicator can be chosen for a particular titration. The progress of an acid-base titration is often monitored by plotting the pH of the solution being analyzed. The plot is called a pH curve or a titration curve. We will spend some time probably Monday going over what a pH curve and titration curve looks like. Now, before I get too far into this lesson here, okay, we'll go over probably this on Monday, what a pH curve looks like, or a titration curve looks like. But I do want to talk a little bit about this. Millimole is just mole with milli prefix. So 1 mole would be 10 to the negative third millimoles. No, wait. 1 millimole would be 10 to the negative third moles. Okay, the reason why I'm bringing up millimoles is because when you're adding a drop at a time, you're probably not adding a lot of moles, are you? And you're probably not using that much volume at a time, are you? So most of the time, we're probably going to deal in millimoles. But remember, molarity is moles per liter the same as a wouldn't that give you the same number? Okay, so we're probably going to deal more with millimoles per milliliter, but it'd be equivalent to the amount of moles per liter because those millis would just cancel out, correct? All right, something that's really, really important here. Now, our first problem. Woo! I'm going to kind of give you an idea of some vocabulary words I will probably use. Midpoint, or another way to say it would be the halfway point of your titration. What that is when you have a 50-50 ratio, or what you have is a ratio of 1. So when you're doing the Henderson-Hasselbalch equation, your log of your base over your acid equals 1. Or 0, I guess I should say. Because your ratio is 1. Log of 1 is 0. What that simply means is you have the same amount of acid as you do base. That's what the halfway point of a titration is, or what they would also might call as the midpoint. Okay, that's when you have neutralized half of your acid or base. Okay, and I'll show you that point when we do the problem. Okay? The second point we're going to talk about is the equivalence point. The equivalence point is when you've neutralized all of the thing you're trying to titrate. So, if I have this, my equivalence point is when I have eliminated all of the moles of acetic acid. So 50 times, well actually I need to convert milliliters to liters to figure that out, but whatever that mole number is, when I've neutralized it all, I'm at my equivalence point. And as we go through this problem, I will show you what points up here we're at those points, the equivalence point and the halfway point. Okay. Questions so far? I'm throwing a lot at you. Okay. So we have acetic acid, and we are going to titrate it with a strong base. I've given you a couple steps that we'll kind of work through and walk through as we do this. Okay? I want to find the pH at all of these points after I add strong base at these increments. Following? All right. The very, very, very first problem. If they ask you to find the pH without adding anything, we're going to treat it like a weak acid problem that we've been doing forever. Because all I have is what? A weak acid. And that's what the first step says. Before any addition of base is added, you're going to perform like a weak acid problem. So, the first step, when we do weak acids, remember how to do low and weak acids? I know we've been doing buffers a while. Remember that? This is the quick version of the ice table. Okay, we would set up the ice table. This should be at my initial concentration. I have none of the rest of it. So you have really x times x, which is x squared over your initial concentration. So square root of your Ka times your initial concentration. Please stop me if you want me to show you that again. Or you guys remember how this worked. Everyone good on that? So when you do that, you should get 0.00134, and how would I find the pH? And that'll give you a pH of 0.00134. So that is the pH of my acid before I add any of my base and begin the titration. Write small, because we got a lot to do. Right? Second step. We have now begun to add some strong base. And so the second step on your little sheet that I gave you, anytime you have added something that you're titrating, but you're before the equivalence point, you're going to treat it like any buffer problem we've been doing up to this point. And all the buffer problems, we did the stoichiometry, then Henderson-Hasselbalch equation, correct? So, we've got to identify the reaction that's going on here. What will react? OH with what? Okay. So my reaction
Which do you include the H or at the beginning?
for this?
Is it just C2?
No, this is not a salt. Does that make sense? This is just your weak acid. And that's, we're dropping a strong base into a weak acid. Now, what it's going to produce is its conjugate. And technically H2O, but we can kind of ignore the H2O. But if you look, what we're doing is we're taking some strong acid, or some weak acid, reacting with a strong base, leaving the conjugate base. So won't I have a ratio of weak acid to its conjugate just like a buffer problem? Okay? We are going to assume completion. Okay? We got to figure out the moles of each, and I'm going to just deal with millimoles. So, to begin with, I have 50 milliliters of Pt1. What that gives me for a millimole number is 5 millimoles. We're going too fast. Okay, then I added 10 milliliters of Pt1. Which should give me, I think, 1 millimole. And how much of my conjugate do I have at this point? Before anything's happened. Right? Okay, I'm going to react to completion. So -1, -1, +1. So that after we're all said and done, that's what we have. And that is our ratio that we use. Now, we do not have to go back and figure out the molarity because it's in the same volume. So if I divide by the volume to both, it's just going to give you the exact same ratio, correct? Like if I take this and divide it by what? 6 60 milliliters and I take this and divide it by 60 milliliters, is that going to change your ratio at all? No. So all I really need to do then is use the Henderson-Hasselbalch equation to find the pH. The pKa of this guy was the same one we've been dealing with for a while, so it's 4.74, and base over my acid, which is my base number. 1. My acid is 4. Your pH comes out to be 4.14. Got it so far?
So you're just saying how the pH changes slide ever so much after?
Yep, after I add a certain amount. It makes sense as I'm adding a strong base that the pH is going to start rising, right? Okay? So, step number 2 on your little sheet says that anytime you're before the equivalence point, you're going to treat it like a buffer problem. And you're going to see that this is before the unit's equivalence point, and this is before the equivalence point, and this is the equivalence point, which I'll show you, how you break that down and know what the equivalence point is going to be. So, I'll do number 3 here for you, and I'm going to make you do number 4. Actually, I'm going to move it over here so I can kind of stay underneath this reaction. So you can kind of see it. Go like that. Okay, all the way throughout, before I get to the equivalence point, isn't my starting millimoles of my weak acid going to be the same? So I'm just going to put 5.0 millimoles. Now I have more of it here. I have 25 milliliters, so I do have to figure out what the OH minus millimoles is. Following everybody. Subtract and add. Is this coming out to be a red flag for you guys?
So that's the same way the pH is being
Mm-hmm. That is your what? Halfway point, midpoint. When you are at your midpoint, pH equals pKa. So, if you can quickly identify your midpoint, do you even need to do all this work? What?
You know, 7.
No. pH equals 4.74 plus log of 2.5 over 2.5, but 2.5 divided by 2.5 is 1, so log of 1 is 0. Your pH and your equals your pKa. So your pH is 4.74. Does that make sense? So when I say halfway point or midpoint, I'm not saying a pH of 7. I'm saying that that's when our ratio is 1, so therefore our pH equals our pKa. Now be very careful. You might be tempted to think, if my volume is half the volume as my starting point, that is going to be my midpoint. It is under one condition. What condition? The concentrations are the same. If this or this had a different concentration, would you be able to make that distinction? For example, if this were 0.2, then you would need twice as much of this to get to that point. Does that make sense? So if the concentrations are the same, your midpoint is when you have half the volume. If the concentrations aren't the same, then it depends on how much the concentrations are different. Okay? So be careful trying to just identify the midpoint quickly with your eyes. All right. Number 4. Same idea. Okay? For the sake of time, I'm going to go through this one as well. Okay, still got 5 millimoles. Now I've added 40. Okay, so this will give me 4 millimoles. Subtracting 4 and adding 4 will give me 4. pH. Of 4/1. Well, a ratio of 4/1, so your pH is going to be whatever that comes out to be, and 5.34. All right. It's a lot so far. Now, notice how everything before the equivalence point, 2, 3, and 4, done the exact same way. Okay, I'm going to tell you right now that 5 is the equivalence point.
If you don't know the sequence, how do you figure out?
You'll figure out as you're getting close. So the equivalence point is when you've completely neutralized all of your initial stuff.
Alright, so if you do it and there's one
So for example, since both of these are 0.1, 50 milliliters is where it would neutralize it completely. So if the concentrations are the same, your equivalence point is when you have titrated the same volume as you began with. Does that make sense? Now, don't always assume that, because could these concentrations be different? Yes. So here's how the equivalence point works. Right? Okay, without trying to write a whole bunch of stuff, right, wouldn't I have 5 of each? Right, if I were to use 50 milliliters here instead of 40, that would get rid of all of my acid, all of this strong base, and leave me with a lot of what? Conjugate base, weak base. So what you are doing when you do a weak acid problem, when you get to the equivalence point, it flips over to a weak base problem. That's what it says. At the equivalence point, perform like a weak base problem, because all of the OH has been converted to a weak base. You don't have any acid left over. So, your weak base is this. It will react with H2O to produce that. Actually, let's see here. I might finish this tomorrow.
Saturday?
Not tomorrow, Monday. Because 5 is the step, or remember 5 through 7 are a little bit trickier. I don't want to rush through it. Cool with you guys? Questions on 1 through 4 so far? Did you feel like you were grasping 1 through 4 at least?
Basically, concentration is different, then you have to figure out
I mean, the same process is still the same.
Yeah, but then
Like you would still go through the before and after, you would still do all this stuff, but you would find that if they have different concentrations, half the volume will not be the midpoint, and equal volume will not be the equivalence point. You'll figure it out. Once you do it, like if you do this, you'll find out pretty quickly, oh, it's equal. Then you can stop and not even do that and just go, oh, pH is pKa. Does that make sense?
So you have to keep going to
They'll always tell you what volumes you're trying to figure it out at. Yeah. So, like in a homework problem, it'll tell you find the pH at this volume, this volume, this volume, this volume, this volume. Usually, every problem will have an equivalence point where you have to figure it out, a midpoint, somewhere before and somewhere after the equivalence point. Okay. All right. Really.